All right, thanks very much for being here. We're going to have 4 speakers. Right now what I'm going to do is just very briefly introduce the speakers and then let them go through one by one. And then we'll have some time for questions at the end for any or all of us. First speaker will be Sandy McDonald from NOAA. He's the director of the Earth System Research Laboratory in Boulder, Colorado, and science advisor for the Office of Oceanic and Atmospheric Research. He's had a distinguished career at NOAA that continues to the present day, and among the many activities that he has, he's the president of the American Meteorological Society. Next up will be Dr. Kyo Takamoto from the Ministry of Environment in Japan, where he's director of the Research and Information Office there. He's had a number of positions in the Ministry of the Environment. He's also worked as a Secretariat Director for the Asia Pacific Network, and he has a PhD from Ibaraki University in Japan. Tom introduced me, and then Phil DeCola, who's the chief scientist at Sigma Space Corporation. He's also taken on an activity for the World Meteorological Organization for the Integrated Greenhouse Gas Global Information System. Before his work at Sigma Space, Phil worked at NASA and the U.S. Office of Science and Technology Policy as a senior policy analyst, and Phil has a PhD from the University of Pennsylvania. And with that, I'll turn it over to Sandy McDonald.
Thanks, Jack. Here's the order of the presentations, and I'm going to talk about the observing network. My talk is developed by Dr. James Butler, who's the head of Earth System Research Lab's Global Monitoring Division. And it's titled Surface-Based and In-Situ Observing Network for Greenhouse Gases. We're located in Boulder, Colorado, and have a long history of a far-flung network. Al Gore didn't actually put the Mauna Loa system up. We actually worked with Scripps on that over the last 50 years, and our laboratory has a network all over the world that I'll be talking about. So the outline of the talk is I want to just say a few brief words about the causes of climate change and the role of carbon dioxide. The main body of the talk is the evolution of the observing networks and the delivery of products and information from those networks. So this chart has been a part of all the IPCC studies. It gets more sophisticated with time, and we've learned a lot over time. So this one, from the most recent one, you can see that CO2, the sort of reddish color on top, is really sticking out as the biggest climate forcer, with positive climate forcing shown to the right. And the total amounts, you see methane is right below it. These are the well-mixed greenhouse gases, and halocarbons, et cetera, all the way down. As you get down below into the aerosols and other chemistry, you see that there's some cancellation with sulfates, for example, negative, black carbon positive. So really the dominant problem is fossil fuels and the growth of carbon dioxide, which is very long-lasting. This diagram shows a chart created by the late David Hoffman of our laboratory, and it shows how our increase of forcing has gone on. And 1990 is taken as the reference year of 1, and the radiative forcing excess over pre-industrial has gone from up almost 40% since 1990. So we are really driving this system, and our job here at COP-21 is to hope that our policymakers can do something about this. This particular chart shows that back in the 1990s, Other gases that were going into the atmosphere were increasing forcing. Notably, the Montreal Protocol made quite a difference, the chlorofluorocarbons. Now it's mainly the increase is mainly being driven by CO2, the fact that those two top lines are very close together. So if CO2 is the primary driver of climate change, what does that look like? Here's the famous Mauna Loa diagram, which is going up very rapidly, pre-industrial of 280 parts per million. We've passed 400. It's basically fossil fuel emissions, and we're lucky enough that about half of it goes into the ocean and other places. However, if you look at the decadal trend through the past decades back to 1960, it's almost monotonic up. There was one decade where it went down associated with the volcano Pinatubo. And we're lucky enough, as I mentioned before, that 50% of the carbon dioxide is captured by the oceans and vegetation. So I want to talk a little bit about our Greenhouse Gas Observing Network and Earth System Research Lab's Global Monitoring Division. It started in the 1970s with Mauna Loa, America Samoa, Barrow, Alaska, and the South Pole. We really just wanted to know something about a latitudinal variation. It became more sophisticated in the 1980s. You see volunteer observing ships giving us a meridional look at it, and flask samples coming in to help us understand the distribution. By the 1990s, we were beginning to want to know what was the global budget, and one of the big questions was what's taking it up? Is it the oceans? Is it the major boreal or tropical forests and so on? So a more detailed network allowed us to do that. And finally, we're talking about in recent years, we're reaching the point where we go from global scale all the way down to local scale. If we're going to have a mitigation policy in many countries, we have to know the details of where the carbon is coming from if you're going to do that. So the Global Atmospheric Watch, sponsored by the World Meteorological Organization, connects NOAA with a international set of players that really can lay out much more accurately the full global carbon by a much improved observing system. And we work very hard with organizations internationally to get traceability so we can compare the various observations that are taking place. For example, there's surface-based networks such as the Integrated Carbon Observing System, of course our NOAA network, the A-Gauge, and the Total Column Observing Network. And all of these are a part of the GAW, Global Atmospheric Watch. So we're here at COP where we're looking at the policy of what do we do about carbon. These observing systems are the foundation that we build our knowledge on what the whole system is going to do. So I want to point out that many countries are adding to this. China has working on an excellent network, Brazil, Indonesia, and these are all crucial. We need to understand these different parts of the world and how they're contributing. Of course, the great West Pacific warm pool, you get observations and help us understand how the tropical forests, which have a really interesting cycle. When you get an El Nino like now, there's tremendous burning of the peat bogs and forests. So we need to understand the details of the system. And we have really important new possibilities coming. Yagos is really instrumenting commercial aircraft. A commercial company in the U.S. called Earth Networks is investing in sites for measuring carbon. And you're going to hear a lot more about satellites in the talks after me, so I'm not going to talk much about it other than saying a global problem requires the global perspective of satellites. So you start with data, but ultimately if you're going to help the policymakers, you have to have the kind of visual and analytical tools that show us what's happening. On the upper left there you see the carbon dioxide is a function of season and latitude, and that red area that you see in the upper left is in high latitudes of the northern hemisphere. During the cool season, there's well over 400 parts per million, and so we have to understand the globe in order to understand what's happening. On the upper right, you see the monthly trends as they vary with northern hemisphere vegetation back and forth, and I've already mentioned the annual growth since 1990. I'll say a little bit about something called Carbon Tracker, which is trying to do a assimilation and full global budget for carbon. Especially you want to think about the fossil fuels, the uptake by the ocean, the creation and vegetation interaction. So Carbon Tracker, we really produce quantitative estimates of carbon uptake and work to really get the details of the global budget. Ultimately, satellites like OCO and our in situ observing have to be combined into models that tell us what the fluxes from the surface are, so that our policymakers can generate policies that will really address the problem. You can't do something if you don't really know what the effect of your policies are. And we sort of have the top down and bottom up. We have people telling us what their emissions are, but we have to go out and measure it and see if what they say the emissions are is really what's happening. So you need an international effort. COP-21 is very exciting in that. The United States is pushing hard to join the nations to really deliver the information that the policymakers need. We have a tough job. It's really just starting to get the kind of details that they'll need in the future. And we know that here at COP-21, we're seeing the results of what we've done so far. My final slide is really showing how you put the whole network together. You start with the current observing stations. You have networks such as the Earth Network, satellites such as OCO that chart give us the column averaged, and of course you put that into models then, and it tells us what the fluxes are and the full global budget of carbon dioxide. So I'll stop there and turn it back over to the next speaker.
Okay. Thank you, Chair. Good morning. My name is Akio Takemoto from Ministry of the Environment of Japan. First of all, it is my great honor and I'm pleased to be invited to have a time to introduce our activities utilizing greenhouse gas observing satellites here. Okay. Today's topic is, after overviewing our satellite, then talking about greenhouse gas monitoring, then observation of anthropogenic greenhouse gas concentration on CO2 and methane, and in the end to talk about a little bit about way forward. Yes, this is GOSAT, greenhouse gas observing satellite. And before my presentation, I was so impressed by the introduction of establishing a network on observation on greenhouse gases, utilizing in-situ data observing tool and aircrafts and ships. And so thanks to the development of such networks, we have developed the monitoring system utilizing the satellite. This project has been conducted by 3 bodies, adding to our ministry from the viewpoint of data utilization, contributing to the policy. JAXA, which has responsible for developing sensors and operation of launching satellites. And the third one is National Institute for Environment Studies of NEAS, which have been engaged in promoting research to make the data from this satellite available for the policy and science. Yes, the size of this satellite extends over 20 meters if the solar panels are open. And the height is over 660 kilometers. Could you please start the movie? Okay. This goes around polar orbit and getting the observation point over 13,000, and it goes back to the original position every 3 days. So after 3 days, like that, it can take the data almost over the globe. Okay, and this satellite can swing the camera so that they could get data as many as possible. Yes. Yes, as I say, compared to the points, number of points on surface observation, it has an advantage, bigger advantage of taking the data more than 13,000. Also, it always needs calibration comparing the data taken on the ground. And another advantage is to get data from the bottom from the top of the atmosphere as high as 70 kilometers. So the data gained from this satellite shows the whole atmospheric information over the Earth. And it utilizing the FTS, Fourier transmitted spectrometers, can absorb the infrared light, and by doing that, we can observe the concentration of CO2 as well as methane. This is the second biggest contributor to the global warming. The summary of the GOSAT 1. It was launched in January 2009. So far, we have measured concentration of CO2 and methane. Then after nearly 7-year observation period, we have established a high accuracy on these data. And adding to measuring the concentration, this satellite can estimate the sources and sinks on greenhouse gases. So this can observe the emission data in each country. And finally, we hope that can contribute to climate change science, such as IPCC reports. I already contribute, but continue to contribute to the next phase. And this is one figure shot to show the annual trends of CO2 concentration in the whole atmosphere. It's not the ground data. But it is quite interesting to compare with the data gained on the ground, so which was introduced by Dr. McDonald. It is it's quite coincidence between ground data and satellite data. But only difference is there are nearly 2 ppm is less when observed by the satellite because it takes the whole atmosphere. And according to the latest information, the monthly average of CO2 reached nearly 398.8 ppm in May this year. And this trend is continue and expected to exceed 400 ppm within the next year. Okay. This is a variation of the monthly average of CO2 from 2009 and 2015. So you can see the April, from left to right, the concentration is steadily increasing from around 380 to more than 400 in the April, which is the highest month in a year. And the second one is the data on the anthropogenic CO2 concentration over megacities. It was, we opened this data last year. So you can see that the vertical axis means data observed by satellite, which means top-down approach. The horizontal axis means data estimated from the greenhouse gas inventory, CO2 emission inventory. So if the data, the point is fit with line, dot line, it means top-down satellite data and inventory data as fit with each other very well. But when looking at the right-hand side, then the data gained in East Asia is not fit with it, which means inventory data is less estimated. So, I hope that in the future we can more detail analyze and to evaluate greenhouse gas data from each country. The second one is same analysis for methane emission. This is very new information publicized just 1 week, just 4 days ago. And we get the same trend in the global average that top-down and bottom-up data is almost the same. But in a couple of regions in Asia and South America, the data gained from satellite is more nearly 1.5 and twice the emission compared to the inventory data. And way forward, now the 3 organizations are cooperating to develop the next satellite GOSAT 2 to be launched in fiscal year 2017, which means early 2018. Then we will add the observation of carbon monoxide and aerosol so that we could more understand the mechanism of the Earth. And the second point is we will to develop innovative tools to evaluate greenhouse gas emissions in nation, and local, and point source scales. Then we will seek international collaboration for greenhouse gas observation with multiple satellites. That will include the satellite operated by US or CO2 or other satellites operated by EU or China or other countries. That will make possible to monitor the more detail on the greenhouse gas emission and also contribute to the modeling analysis and the mechanism of climate change in the future. Thank you very much.
All right, what I'm going to do now is to say a little bit about some of the things that we do at NASA for studying the Earth's carbon cycle and really how we go from observations to products and looking at the full carbon cycle, not just the carbon that's in the atmosphere. So I'll do a brief introduction, say some things about the satellite observations that we do, also some things that we do with airborne observations and related field work, a little bit where modeling fits in, and then putting the pieces together, providing data products that comes out of activity that we call our carbon monitoring system activity, and then I'll sum up. So for NASA, really, it all starts with the satellite observations, and we try to, for the carbon cycle, to look at the observations that we have now and the observations that we're going to be having in the future. And that's a lot if you look at the list. The Orbiting Carbon Observatory that's been mentioned, some things that would be coming in the future, ISAT-2, the NISA and NASA Israel Synthetic Aperture Radar partnership with Indian Space Research Organization, OCO-3 to go on the International Space Station, also Global Ecosystems Dynamics Investigator, PACE satellite for studying oceans. We're making some early stages to potentially lead to a LiDAR measurement and hyperspectral imager, as well as a lot of things that are out there coming from interagency and international partners. We draw on all of them and learn from the advances that they make. If you look at the fleet of satellites that we have right now and the ones that we're looking at in the future, and the different colors in the labeling represent the different stages of the mission: primary operations, extended operations, implementation, or formulation, or pre-formulation. A lot have carbon as a significant part of what they do. The circles and ellipses represent the ones that we think are most involved in carbon, and the ones that are dashed are involved, but maybe not quite as involved. You can argue about sort of where to put the circle, solid ones and the dashed ones, but the point is that a significant fraction of the fleet that we have is making observations that are directly related to the carbon cycle, and that's going to continue in the future. The Orbiting Carbon Observatory, this one may need to get clicked on to start running. It's been up for about 1.5 years, so just recently they started releasing the products. It shows the variations sort of over a couple of week period, and then you get more observations in the brighter lit hemisphere. So in the winter, the emphasis is on the southern hemisphere, and then as you get into spring, it'll work its way up to the northern hemisphere. You get to the begin to see the spatial variability and the temporal variability, and how what you're looking at will vary with space, with time, looking at the seasonal impacts, and recognize that it has to be a very high precision measurement. This is true of all the space-based CO2 measurements, because you're looking at relatively small variations against a fairly broad background. So the metrologic aspects of the mission are quite significant. From an airborne and field activity, there's a lot of work that we can do with airplanes which serve to help bridge the scales between surface-based measurements and the satellite measurements. And there's some that we've done, some that we're going to do, as well as some smaller things that we've been looking at, and some things we're looking at in the future. And I'm going to very quickly run past a couple of those because it gives you a sense of the diversity of the things that we do. And I'm not going to show details on all the ones that I have listed. But CARVE is one that we've wrapped up. The airborne acquisition phase. It's been flying quite a bit in the Arctic to measure information that will help you get the CO2 and methane fluxes. It's a sort of a low and slow plane that'll measure both in situ and column measurements. So there's a lot of measurements in Alaska or over Alaska, trying to look at the times when you would expect to have emissions and to see how they vary seasonally and how they vary from year to year. And so from the point of view of over a couple of different years, that there's been quite a bit of coverage in different directions from Alaska. So a few papers are coming out, but the data set is really now what's beginning to get out there for scientific use. We recently selected 6 suborbital Earth venture investigations, and those are multi-year, typically about 5 years, with data acquisition over 3 to 4 years, using a variety of aircraft going to a variety of places of the Earth. About half of them really have a significant carbon component to it, and I'm going to, show information about 2 of them. One is ACT America, led by Ken Davis at Penn State University, which is going to try to make quite a few measurements based in the continental U.S. to really look at atmospheric concentrations of CO2 and methane to try to really be able to zero in on what's the exchanges between the surface and the atmosphere. And that's sort of trying to get at the exchange of carbon between the atmosphere and the surface biosphere is an important aspect of what we do. Another one is NAMES, which is looking in the North Atlantic Ocean, the NA for North Atlantic, studying the plankton cycle, because that's really what's associated with the uptake and ultimately release, but especially the uptake of carbon in the North Atlantic Ocean. And then we can make the interdisciplinary connections between what the plankton do in terms of then compounds that get into the ocean and then the atmosphere and how that can affect atmospheric aerosols. The ship just left on that one. They had the airplane flying, got some of the first observations, and I think bringing the plane home. And the new field campaign that we'll be starting is the Above campaign. We'll start with a ground-based activity and then bring Airborne to look at it's the Arctic boreal vulnerability experiment to really get out on the ground in Alaska and Northwest Canada to be able to see what's happening, especially looking at vulnerability, resilience of ecosystems to environmental change in the Arctic and boreal regions. And so when you look at sort of some of the primary areas, it's Alaska and Northwest Canada and some secondary areas. There'll be people on the ground. We've selected, I think, 22 different teams to be part of it, and we'll be soliciting next for an airborne component. We've been doing some airborne work for methane at a sort of very experimental level using a couple of new sensors, sort of trying to work their way from sort of very specific locations to a little bit broader. But the fact that we've got two new sensors, the Avarice Next Generation and the HITEST, it's a hyperspectral infrared going out into the mid-infrared and thermal infrared, that we're really looking at what can we do with methane, and especially to make the connection between smaller scales and broader scales. We're doing some models, simulations as well, and if you click on that, I'll just show you very briefly an example of some very high-scale carbon model simulations that's been done at the Global Modeling and Simulation Office at the Goddard Space Flight Center, looking at both carbon monoxide with sort of the white and carbon dioxide with the colors. The point now is that with these models, we can incorporate and assimilate observations from the surface or wherever else. This was very high resolution, I think a 7-kilometer model. So we're really beginning to be able to integrate observations and models in ways that we haven't before. We do have a carbon monitoring system that we call it. It's a small program that really builds off everything else that we do to try to find a way to leverage the investments that we have in observations and fundamental research and be able to provide products for community use to really study how carbon is behaving. So we especially want to look at stocks, what's in above ground biomass, and what are the fluxes, how is carbon being exchanged between the atmosphere and the biosphere. The three parts, biomass, flux, we had some pilot projects early on, now trying to move into a more extended effort, but also to do some scoping studies and user engagement to understand what kind of products do people find useful. So we've developed a biomass pilot focusing on the continental U.S., where we use imaging satellites, local airborne LiDAR observations for the vegetation canopy. So again, the theme is to connect what's taking place on the ground to what we see in the atmosphere. And then the flux pilot, we're really trying to look at what we know about the land, what we know about the ocean, and what we know about the atmosphere. And again, to make that connection between what we see taking place on the surface and how that varies spatially, seasonally, and interannually to what we see in the atmosphere, and really pulling that together. And I'll conclude. So we see the satellites both individually and in conjunction with those of our partners are making important contributions to understand the global carbon cycle. Integrated surface atmosphere field campaigns help us understand the processes and help us bridge the scales between smaller scale activities at the surface and the broader scales that the satellites do. The modeling is going to help us integrate different kinds of observations, pull the pieces together, and that can help us both produce products, but do quantitative tests of hypotheses. And the products that we have that build from the observations will be made available, shared to the community, sort of to individual scientists, researchers, but made broadly available and through our partners. And with that, I'll stop and turn it over to Phil DeCarlo for the last presentation.
Okay, thank you. I have my phone with me here, not so that I can tweet about my presentation. I'm not that talented to do that, but just for the time. Jack already introduced me. I'm here today to represent a project that knits together a lot of what you've already heard about from my co-speakers. It's a process that's being spearheaded by the World Meteorological Organization, and in particular in the area called the Global Atmospheric Watch, which is part of the Commission for Atmospheric Sciences. And I have a number of co-authors of this presentation, Riley Duran, who is both the lead of the Megacity project, which you'll hear a little bit about. Plus, Riley has also been a lead within the carbon monitoring system program that Jack just mentioned, in terms of looking at stakeholder engagement and how we can get the most out of these scientific research and observation and modeling capabilities that we've developed to deliver benefits to improved information for decision-making, evidence-based information. Jim Butler and Oksana Tarasova, Jim from NOAA, ESRL, where Sandy McDonald's from, and Oksana, they really were spearheading this idea of an integrated global greenhouse gas information system for a number of years now, and it's coming to fruition. Jack mentioned the carbon monitoring system program. A lot of the ideas in this have also come from the growth of ideas coming from that program. And James Whetstone from the National Institute of Standards and Technology has been a leader in understanding the value of focusing on the urban domain for greenhouse gas mitigation and monitoring. Oops. Okay. So looking back to 2010 and the Copenhagen COP, at that time the process was very much still a top-down process where there were commitments that were going to have to be verified in some way. And we weren't making much progress. In fact, that Copenhagen meeting broke down around the whole issue of verification in part. And around that same time, the scientific community began to think about how we can use what the atmosphere is telling us to perhaps verify what the bottom-up inventories that come from activity data and emission factors are telling us when looking at energy use to determine what the fluxes are from either economy-wide assessments or sectoral assessments. And so there was a National Academy report verifying greenhouse gas emissions. There was the geo-carbon strategy. And then this one on the far right was a meeting in the same time where we brought together the IPCC task force community that develops the bottom-up protocols that are used for country reporting, together with the research community to see if there was truly an opportunity to work together to create improved a posteriori information from both the bottom-up and the top-down. But the top-down, in terms of monitoring, was a new concept at that time. So now here we are in Paris, and coming out of Lima last year, we have a new process now that's more aspirational and bottom-up. We understand that it's not going to get us on the virtuous path that we'd like to be on, but at least it has everybody invested. Everybody's got a chip in the pot. Everybody's going to ante in, and hopefully over time, those bets will be raised and we'll get to where we need to go. And at the same time, we've evolved in our understanding of how observations and models from the research world can play a role, and that's where this integrated global greenhouse gas information system comes in. So it's evident now that nations, states, cities, private enterprises are all interested in looking at ways to reduce their emissions, but you can't really understand the efficacy of the policies that you put in place if you're not able to measure and really have good information, evidence-based information. And so this past June, the WMO held its quadrennial Congress where 191 national meteorological, hydrological services come together to discuss the programs for the coming 4 years. And there we presented a resolution for planning this integrated global greenhouse gas information system. And one might ask the question, why should WMO be involved in such an enterprise? Well, you already saw this slide in Sandy's presentation, but there are a number of reasons. I'm going to highlight two. One is that the Global Atmospheric Watch, which is part of the Commission for Atmospheric Sciences in the WMO, is the standard bearer for greenhouse gas observations. They control not only the standards and establish them and propagate them, but they also are responsible for archiving and distributing the information and getting the word out with the Greenhouse Gas Bulletin to inform everybody about what's happening with the progress of the concentrations of the atmosphere. Another reason why WMO plays a role can be seen here. If you look on the left-hand graph, you can see in the case for some work that we're doing in Boston, monitoring greenhouse gases in the Boston and Northeast Corridor area, you can see that at night there's this, we measure near the surface a very elevated concentration of CO2. However, as we approach morning, you can see that that concentration that we're measuring at that point location is dropping just as the rush hour in Boston is picking up and the fluxes of CO2 from transportation are rising rapidly. So how is that? Well, what it is telling us is that really the dynamics of the atmosphere is a critical piece of information that we need. As the sun rises, of course, it's heating the surface and creating turbulent mixing in the boundary layer of the atmosphere, and the mixed layer is growing, so the concentrations go down due to dilution as the mixed layer rises in the atmosphere. And we really need to understand the transport and dynamics of the atmosphere as well as make measurements of the concentration if we're going to be able to get at the quantities that we're interested in. So back to this chart again. So what is it that we need to be successful? Well, first of all, we've begun to realize through the work that Riley has done through CMS that we really need to be specific about information for whom. Who are we building this system for? And what is it that, what information and for whom? And then where do we have credibility, scientific credibility, and also where do we have a value proposition where the retirement of uncertainty really is going to pay dividends? And we know we're going to need to fill gaps in observations. We're going to need to build partnerships with, say, for example, the air quality community, who's making measurements already in the large source regions. And we're going to also need to go from just economy-wide bottom-up inventories. We're going to need to make progress in data mining and get towards more temporally and spatially explicit inventories to go into the whole mix of the top-down, bottom-up integration. And also we need to align with the policy that has been laid out here for COP-21. We align very nicely with the INDCs, as I mentioned already, and also with the reporting mechanisms in terms of improving inventories. And then also the Lima Paris Action Agenda is one that is really well suited to the way that we're building this IGIS, this Integrated Global Greenhouse Gas Information System. And I'll give you an example of that in a moment. In fact, I'm just going to jump to it. You can see here, again, aligning with the 4 pillars, we have inventories that we're hoping to improve. We have the ability to help sectors and localities who have policies in place to know what the efficacy of those policies is. and then also our ability to help mitigation specifically by finding, for example, large fugitive emissions coming from the oil and gas supply chain of methane. If natural gas is truly going to be a successful bridge to a renewable energy future, then we're going to need to be able to keep the leakage from that system low. And so we're able to use observations and models to help find those fugitive emissions, and then they can go out into the field and turn them off. So historically, the Global Atmospheric Watch has been focused on the background atmosphere. And as I've already indicated, we're increasingly moving towards increasing observations, investments in new observations in the large source regions. The megacity project, which has started with 2 cities, Paris and Los Angeles, is an example of that. Why isn't it? Okay. And cities matter for a number of reasons. One, because that's where the action is. 70% of the problem is coming from the emissions from these large source regions and their supporting infrastructure. You can see the same image not only from the flux in the Edgar inventory, but also from the night lights. Cities are also where there's political will. They really are responsive to the Paris-Lima agenda. The cities have very ambitious goals, as seen in the LA's plan, 35% below 1990 levels by 2030, and it's where the problem is growing and getting more and more challenging with population and urbanization. And it's also a tractable problem. You can see that as you get down to finer scales, the signal becomes stronger. The far left is Indianapolis, and those images really are coming from new data mining techniques of Kevin Gurney at Arizona State University. Here's Los Angeles, and you can see from this inventory at the human scale down to the street level and building level that most of LA's emissions are coming from transportation sector. And ultimately, if we're going to have the urban agenda as helping us and is one of our IGUS initiatives, we're going to need to understand how many different types of cities are there, how many different protocols and networks are we going to need to develop in terms of spanning the space of cities and defining the typology that we need to capture to be able to do this work. A couple more charts here. I've mentioned that we're going to have to move from the global background observations in situ to the source regions, the large source regions. And in space, we've already seen many examples of how we've demonstrated the ability to make greenhouse gas measurements from space. In the future, we anticipate that there will be either or both geostationary and low Earth orbit capabilities that will allow us to stare and avoid the fact that and get around the fact that we live on a very cloudy planet, and that sometimes doesn't allow us to be able to see down to the surface where the action is. But from geostationary, we can wait for the clouds to move and stare where we need to stare. And also from low Earth orbit, we can use more wide swath mapping capabilities. And here's an example of the different kinds of footprints that can be obtained from different instrument concepts. Jack showed this slide already, and the only reason why I'm repeating it is we don't prescribe what observations are going to be critical. We want to look at what the use cases are first, and then drill down into the how. We don't want to start with the how. This is my last slide. It's a summary slide. I'm not going to read through the whole thing, but I want to focus on a couple of key points that, again, we really need to entrain, not just engage with stakeholders. We need their participation right from the beginning. Otherwise, we can't possibly be successful. If we think that we're going to be generating information and we just write a report and hand it off at the end of the day, that's not going to work. We need to build trust and confidence that we have the credibility that meets the use case and that has a value proposition associated with it. And we don't want to just build more and more science reports, grand research strategies. We want to drill down and be practical and really develop some confidence that we can build examples of end-to-end information systems. And I'm going to stop there. and thank you very much.
Thank you, everybody. We do have some time for some questions. I do want to tell everybody watching online to please ask questions using the hashtag AskUSCenter. So does anyone have a question for our panelists? Don't be shy. Well, I have a question to ask. In the beginning, you mentioned how there could be commercial aircraft that do, at least, can you describe how that sort of relationship came about? Who approached who, and how do those sorts of relationships develop?
Yeah, there's a long history that started actually with the commercial companies wanting better weather predictions and giving the meteorological community winds and temperatures, which then go into the models and result in better weather forecasts. In recent years, particularly Europe has been a leader with working with the commercial companies. It's a more complicated thing because you've got to put in a system that actually uses the ingest of outside air into the aircraft as it ascends and descends, and even at flight level, and does a chemical analysis and feeds it back. And these are being looked at by the United States, also in Asia, and really Europe is the leader in that.
One of the objectives that we're looking at as a possible recommendation in the Integrated Global Greenhouse Gas Information System is to expand that activity, because if you have greenhouse gas measurements in addition to the measurements of water vapor that are already in play for mesoscale weather forecasting, you can get many profiles in and out of urban areas every day if you have them on intracontinental aircraft. And with those profiles from about 11 kilometers down to the surface, we can really tackle the big uncertainties that are remnant for transport, atmospheric transport, that's going to be a critical need for us in improving our ability to constrain fluxes of greenhouse gases.
Do we have any other questions?
I'm interested in the carbon typology of cities, and I'm wondering, sort of off the top, if you could run through a few different types of, what those might look like.
So some aspects of it are geophysical. For example, Los Angeles is a city, of course, that's complicated from an atmospheric dynamics perspective, in the sense that it's ringed by mountains, and it has a frequent marine layer that comes in off the ocean. So the boundary layer dynamics are very complicated. You've got flow coming off the mountainsides, and then you've got, in the case of LA, like I showed, that really transportation is the largest part of its human component. Then you've got and it's also tends to be more of what we call an urban dome. In other words, you get an inversion layer that really persistently captures the buildup of the greenhouse gases. So that's one example. Then Paris, for example, is more of what we call a plume city. It's out on a plain. It's not ringed by anything that's containing it. And so we have to really understand the inflow and outflow to be able to capture what's happening at the surface in the case of Paris. Then you've got a variety of others, and the question is, what's the irreducible representation that spans the space of types of cities that we're going to need to be able to characterize? And each one will have a different network type, for example. And that's really the kind of analysis that we're starting to do now.
So I want to introduce our information observed by the GOSAT satellite. This satellite can estimate the greenhouse gas concentration over megacities emitted by human activities. For example, it detected the concentration over Los Angeles is about 4.5 ppm, while Pittsburgh 2.1, and Saudi Arabia 1.8, Kolkata of India 2.0, So that can be detected, and adding to the information observed by the satellite, then also utilizing the modeling analysis, the air mass transformation. So also that we need to more do a research to reduce the error, but in the future we can get a more detailed data. And also, yes, that's right. And also, our country also do the aircraft observation utilizing the JAL airplanes between Tokyo, European countries, and Australia and USA, and that can get very important information. And adding to the data gained by US countries, we can have a more detailed greenhouse gas observation. Thank you.
I was just pulling up an example of GOSAT from early data analysis by Eric Court, who's a professor at University of Michigan, where he was able to show that there's a persistent bias, not unexpected, but that from space we can see the pink observation footprints in the core of the city, and then the two red observation footprints outside of the LA basin, and you can see that there is a persistent gradient that can be observed from space with GOSAT, and we're going to get more and more skill using these kinds of measurements as we go forward.
Great, thank you.
Thank you for that. We have time for one quick question. Okay.
Good morning, Karim Hilmi from Morocco. Thank you for the distinguished professor for their presentation. I would like to know if you have some specific programs of research for developing country, mainly for the North African countries, and in ocean specific thematics. Thank you. It concerns the NASA and GOSAT and so on. Thank you very much.
Okay, let me say, your point is, do we have any plan to cooperate with developing countries to detect more information on the greenhouse gas emissions and concentration? Okay, yes, one of the aim of this GOSAT project is to assist developing countries to promote climate change mitigation policy through the improved MRV system to measure the carbon emissions from the nation as a whole, but also the local areas and point sources. By doing that, we can check the volume of the emissions more correctly with combining the data on the ground. So and then we can cooperate with developing countries, nations to promote their activities. Maybe I guess that many countries don't have detailed, precise database on emissions, and also database on economic and social activities. So I hope that kind of information through the top-down approach could help assist such developing countries. Thank you.
I would like to add that we can use, where the data isn't available readily for taking advantage of new data mining techniques, we can use remote sensing to help identify activity data and emission factor data. That's one way, but in general, we really need to work on capacity building to build up that kind of capability to understand what is happening on the ground, especially in large megacities in developing countries where there's a lot of growth of population and growth of the urbanization, and that we're really going to need to have better information, and we're going to have to work to propagate these new capabilities of data mining in the developing world.
Thank you, everybody. Can we give the panelists another round of applause?